Hey Brian, you want to build a Michelson Stellar Interferometer?
Is that it?
So the purpose of a Michelson Stellar Interferometer is to take two incoming waves from two different sources that at a specific Rayleigh criterion cannot actually be distinguished between one another, as shown through these images, where there's really two sources, but at specific Rayleigh criterion there is only one source visible. So this is the classical setup of a Michelson Stellar Interferometer, where it shows the two different waves coming in at some angular separation and being imaged down through reflections and refractions through pinhole onto an observation plane to create fringes of equal thickness. In this interferometer setup, changing the separation D, as outlined in the image, will change the fringe spacing itself. And then changing H, the mirror separation, will change the visibility. In our setup, what we have used is two laser diodes through a beam splitter, through a lens, going through a cylindrical lens, creating our two slits, which effectively is like our stars. And we are adjusting this slit so that has a different variable in our D. However, since we are changing both visibility and fringe spacing simultaneously, we are going to be measuring the effect of the visibility versus fringe spacing of just this slit. It then is imaged down to a microscope objective and seen through a detector.
For our setup, what we did is we used two laser diodes to simulate the incoherent light passing through the beam splitter. We then used a positive lens to collimate the light coming from the beam splitter. Instead of using a single slit to condense the laser light down, we instead used a cylindrical lens to take the collimated light and squeeze it down to a fine line. That line then passed through the double slit and through another positive lens. The laser light was then magnified using a microscope objective and imaged onto the camera detector.
What happens is when, after resolving the 2 point sources, we should see that the two light sources going through the slits will create interfering fringe patterns due to the incoherent light that they cause. And by moving this slit spacing, by increasing it, what we should expect to see a decrease in the spacing between the fringes themselves, and also we should expect to see a decrease in visibility.
When the 2 points could no longer be resolved with one another, or at the very edge of resolution, the aperture stop was at 6.0452 millimeters, which leads to a Rayleigh resolution of 40.8 microns, which is the distance between there and there. When we were calculating our fringe spacing, we compared the theoretical fringe spacing to the experimental fringe spacing. And so theoretically what we did is f lambda divided by d, which led us to a theoretical fringe spacing of 4.75 microns. Now we took the exact same fringe spacing and we applied it to the experimental fringe spacing, where we measured the pixel width and applied that of one fringe spacing, and then applied that to the resolution of the camera and divided it by the magnification of the objective. And that gave us 6.695 micron, which led us to have a percent error of about 40.9%. And this could be caused to many different things such as noise, slight misalignments, the detector being very sensitive, reacted to different things in the environment.
What we saw from our results is that when our slit width was increasing, our visibility was decreasing. And as you can see by our graph, that's what our data did show.
A little bit of error with the calculating the visibility is that if you look at this graph right here, that has no real axes labels. You pretty much just have to guesstimate at that point in time. We tried converting it to MATLAB. In general, they had some weird scaling errors as well as shifting errors that when we calculated it said that the visibility is increasing. We know for a fact it isn't.